In today's lesson, we are going to be talking about the difference quotient. Now, you may have seen the difference quotient before in the past. You may have learned how to use it or learned how to simplify something using the difference quotient, but you may not have understood maybe the background behind it or its applications or what exactly it is that you're finding when you're finding the difference quotient. So today, before we get into what the difference quotient is, we're going to first start out by talking about slope. Now, slope, as we've talked about it before in the past, as you've probably learned about it in the past, slope is simply the steepness of a line. Another way to think about it is the rate of change of a function. It's the ratio of the vertical change to the horizontal change. So for a line, that's pretty straightforward. It's simply the change in y over the change in x, and that gives us the slope. Now here's the thing. Not all graphs are going to be lines, but we still want to be able to talk about the slope or the steepness or the rate of change of that function. So when we talk about rate of change more generally, we can talk more generally about graphs in general. So a curve also has some sort of rate of change, but the issue is, unlike a line where the rate of change is a constant rate of change, right? No matter where you are on a straight line, that slope is the same. On a curve, the rate of change is different depending on where you are. So here's an example, right? You have a parabola, and you can see that the rate of change is negative on the left-hand side, and it's positive on the right-hand side. And then right in the middle, actually, the rate of change is 0. So when we talk about rate of change, we want to be able to talk about rate of change with respect to anything, including curves, where the rate of change will be different depending on where you are on the graph. Now, it is possible to calculate the rate of change at each point on the graph. How do you do that? Well, the rate of change is going to be the slope of a line that is tangent to the graph at that specific point. Now, a tangent is, just as a reminder, the straight line that, quote unquote, just touches the curve at that point. So here's an example. That red point right there, if I wanted to know what the rate of change was at that specific point, then I would just draw a tangent line, the red line that's drawn here. Whatever the slope of that line is going to be the rate of change at that point. Now, how do you go about finding this line, right? Well, we have to think about this as a whole, right? We have a curve that's defined by some function. And so in order for us to find the slope of the tangent line, it's going to be different if you are at a different place in the graph, if you have a curve where that rate of change does change. So how do we do this? So here's an example just so you can see how that tangent line is different as you move along the curve. So there's this calculus concept called the derivative, and the derivative allows us to calculate the slope of a curve at a specific point. And we call the slope at a specific point the instantaneous rate of change. Well, we know in order to find the slope of a curve at a specific point, we need to find the slope of the line that's tangent to the curve at that point. But the problem is we only have one point, right? Normally when you find the slope of a line, you have to have 2 points so you can find the change in y over the change in x. But if we only have a specific point at which to work with, then what do? Well, we're going to use a different type of line to help us out, and that's a secant line. Now, a secant line is a line that touches a curve at 2 points. And so here in this picture here, our graph is the blue one, and then the green line that's going through that in 2 points is the secant. So if we use this, now we actually have 2 points to work with, and we can actually find the slope of the line, right? The slope of the secant line. So just as another picture here. So here in this case, say you're trying to find what the slope or what the instantaneous rate of change is at that black dot. But since you only have 1 point, we can't find the slope. So we draw a secant line, so the secant line is very close to the tangent line, but it goes through the graph in another place. So because it goes through the line in one other place, then we can actually find, okay, here's x, here's f of x, here's x plus h, and f of x plus h. So we have your x and y coordinates for both points. And if you have that, well, then you can actually get a slope. But you might be thinking, well, but that's not the slope, or that's not the instantaneous rate of change where the black point is. It's a little bit off. So this is where the difference quotient comes in. What we want to do is we want to make that gap between x and x plus h approach 0. So here's an animation here. So the closer and closer you make that red point, the closer it is to the black point, the closer it is to being that tangent line. And that's what we want. So what does this mean for us? Well, in calculus, you will be finding the slope of the tangent line by finding the slope of the secant line as h gets really, really close to 0. The language that's used for this calculus concept is the limit as h approaches 0. Now, a limit is the behavior of a graph as it becomes closer and closer to a certain value. So as h approaches 0, that means as that point, as that red point gets closer and closer to the black point, what is the slope of that line? So if h is exactly equal to 0, then you can say, well, if h is equal to 0, that means that we have exactly that line, that tangent line. So here's where the difference quotient comes in. So this is just the picture from before. We have 2 points, and if you are trying to find the slope of the secant line, then you would do y2 minus y1 over x2 minus x1. And y2 is f of x plus h, y1 is f of x, and then x plus h is x2, and x is x1. And then simplifying the denominator, the x and the minus x cancel, that leaves us with h in the denominator. So this gives us the slope of the secant line, and generally, when we use the difference quotient, we can find something in terms of h, and then if you are looking for the slope at a certain point, you can plug in the value for x, and then you can make h equal to 0, and that will give you the instantaneous rate of change at that specific value of x. So let's do an actual example where we actually apply the difference quotient. Hopefully that gives you a little bit more context in terms of what it is you're actually solving for. The difference quotient is actually just the slope of that secant line, and then if you were to get an answer for the difference quotient and you wanted to find the instantaneous rate of change, you would set h equal to 0. Okay, so for f of x equals x squared minus 4x plus 7, find f of x plus h minus f of x all over h, which is the difference quotient. Okay, so applying this, we are going to plug in x plus h into x to get f of x plus h. So this will be x plus h squared minus 4 times x plus h plus 7. All right, so I'm just taking the x plus h and plugging it in for x. Now I still need to subtract f of x from that. So that's x squared minus 4x plus 7. So I have f of x plus h here minus f of x. And on the bottom we have h. A lot of the work here is just having to do the algebra out. So this x plus h squared, that's going to be x squared plus 2hx plus h squared. Distribute the minus 4, so minus 4x minus 4h plus 7. Distribute the minus to the f of x, so that's minus x squared plus 4x minus 7, and then all over h. All right, find anything that cancels out, so x squared with the minus x squared, minus 4x with the 4x, 7 with the minus 7. That leaves us with 2hx plus h squared minus 4h all over h. Divide everything by h, and that leaves us with 2x plus h minus 4. Now that's the difference quotient. In terms of, well, what if I wanted to know what the slope was at, say, x equals 1? How do I do that? Well, then you would plug in x equals 1 in for x, and then you want h to equal 0. So it would be 2 times 1 minus 4, and that would give you negative 2. So you know that the instantaneous rate of change at x equals 1 is negative 2.